Good morning, good afternoon, everyone. My name is Raman Sridharan. I am Product Manager for Vibration Controllers at Data Physics, and welcome to the Coffee Break webinar series on understanding the pretest report in SignalCalc 900 Vibration Controller. So the agenda for this presentation, for this quick demo here, is going to be to understand the purpose of the pretest report, to interpret the pretest report, and we're going to show you the functionality known as auto-shaped pretest that we have in our controllers. And then we're going to show you some demos and show you how to use the pretest report in order to predict problems that you're going to have running a test before you actually start the test. So the pretest is both a safety and a diagnosis tool. It's run before every single vibe control test. And the way that the pretest works is we excite the shaker system with a very low level excitation. And that low level excitation is then used to do various things. The first thing is we verify that we get a closed loop response from the accelerometer, from your control accelerometer. We measure the signal to noise ratio. We determine the appropriate level for the pretest to run, and based on that signal to noise ratio. And then we actually make vibration measurements based on that low level vibration. And from those vibration measurements, we get predictions on how much drive voltage we're going to need to run the test, predictions on how each of the control accelerometers and each of your response accelerometers are going to respond when you're running your full level profile. And we get predictions if any of your channels are going to be overdriven, either your shaker be overdriven, or your input channels, your accelerometers, if they're going to read too high of a G level. We'll get a prediction of that in the pretest report. So all of this information is put into a pretest report. I'm going to go through that with some demos here, and we will go through all these bullet points with the live demo. So I have a couple demos set up here. Let me switch to my demo software, or my 900 series software. So for those of you that aren't familiar with the 900 series software, we have other tutorials and other videos on our YouTube that cover the software layout and how to access and save data and open tests and things like that. I'm going to focus here on the pretest today. And I've got a simple random vibration test that I'm going to be running with. So just to show you where the pretest setup is, in my test setup, if I go to my random vibration setup, at the right side of my control parameters tab, there is a pretest section, and that shows the settings for the pretest. So the excitation mode for the pretest, we're going to start with the standard broadband excitation. And I'll get into the auto-shape broadband at the end of the presentation. That's a newer feature that we have had in the last year that dramatically improves the quality of your pretest data. But we set a signal to noise threshold that we need to see at least 12 dB of signal to noise ratio before we actually run a pretest. And that signal to noise is monitored on either just the control channels, the control and limit channels, or all of your accelerometers. I mentioned the pretest is a very low level vibration signal, or a voltage signal that we send to the amplifier to tickle the shaker. And these are those low levels of voltage. The start voltage, this is in peak volts, so the RMS is going to be about 1/5 of this. So we start out sending this many volts, and we will bump up that voltage until we hit our max voltage, or until we meet our signal to noise criteria. If we meet our signal to noise criteria, then we are going to run 12 averages, or however many averages, at that drive level. If we hit our max voltage before we hit our signal to noise criteria, then we're going to abort the pretest and say there's something wrong. Either you don't have there's a problem detecting the closed loop feedback. All right, the couple of other settings here are the minimum coherence and the minimum coherence threshold. The minimum coherence is after the pretest is done, we look at the coherence value of your control signal. And I'm going to get into the coherence value when I'm actually running on the shaker here to give you an idea of what that actually means. But a coherence is basically a measure of the controllability or the linearity of your shaker and test article and accelerometer system. And if your coherence is 1, that means it's perfectly linear. You can control it very well. If it's 0, that means you have no chance of controlling it. It's basically behaving completely independent of how we're driving it. So we'll see that coherence signal on the plot here and on the plot during the pretest, and it'll give you a good idea on how to debug something if something goes wrong, or when something goes wrong mechanically usually. But the setting here in the software is saying I want to have at least a coherence of 0.5 for 90% of my frequency range. So my pretest is going to run, I start outputting the start volts, I increase until I hit my signal to noise ratio. I run my 12 averages, and then after that, I look at my data, I look at my coherence value, and if my coherence value is less than 0.5 for 10% of my frequency range, then the pretest is going to fail, and it's going to tell me that I need to work on my my structure, and something's mechanically wrong with my structure. All right, so our default settings in the run test tab here, our default settings are we display the pretest transfer function, the pretest coherence, and then the time domain of your first accelerometer. These are generally the, most of the time, these are all the plots you want to look at during the pretest. If you're running a lot of channels or a very large test article or very large shaker table, you might want to add some more measurement channels so that you can see what's going on at different points in your table to isolate different problems. But I'm going to stick with this here. I've got a small desktop shaker with 2 accelerometers mounted on it and a large beam mounted across that on that shaker. So I'm going to see the click initialize and start, and the first thing that's going to happen is going to measure the noise. It's going to start measuring my data, and it's going to bring up my pretest report popped up on my other screen. So I'm going to push the pretest report to the side for now and just show you what the plots the pretest generate. The first plot is the pretest transfer function, and this shows you where your resonances are, where your anti-resonances are, and it gives you a lot of dynamic information about your shaker and test article. The bottom plot here is the coherence plot, and this shows you exactly what the coherence value is for each frequency band. So you can see I've got some pretty good coherence here. It's about 0.8, which is generally pretty good across the whole frequency band. And I've got some dropouts here. And in general, you only want to see a dropout if you have an anti-resonance here. Then you'll see a dropout on your coherence. And the other place where you see dropouts like coherence are if you've got something rattling or something generating noise on your shaker. You'll see a drop in coherence in your coherence plot. And that's something that may or may not force the test to be able to be run. But the idea with the pretest is you can visualize that before actually going to run the test. You don't have to start shaking really hard before you can identify those potential issues. The third place you usually see a drop in coherence is at low frequency, and this is generally a problem with shakers. If you drive them with white noise, as we are in this pretest, you get lower coherence at lower frequency compared to if you drive the shaker with compared to the response you get at higher frequency. And that's because the shaker responds with less force, less acceleration at low frequency. And that's just typical of most shakers. So now I'm going to pop into my pretest report, and I'm going to go through the different settings that are displayed, the different results that are displayed. So the top left corner shows the pass or fail criteria. Did I detect my closed loop control? In this case, I did. The top right corner shows, do I think based on the data in my pretest, do I think that I can run this test on the shaker given the drive limitations and given the accelerometer vibration detection voltage limitations? Can I run this test? And that says pass, which means I can. Then down in the bottom, it gives you a really detailed, granular look at what we predict is going to happen during the test. So the first row here is your drive. So the drive going to the amplifier. Now it predicts in my ramp up stage, I'm going to need 35 millivolts of drive. And at my full 0 dB test stage, it's going to need about 140 millivolts of drive. And this is all a prediction based on this data that you see behind the pretest report. So if I had a lot of mass on my shaker, or let me do this. Let me hit abort here. And let me turn the gain down on my shaker. So I'm turning the gain all the way almost to 0 on my shaker. So it's going to require a lot more drive to run the same exact vibe profile. So let me run another pretest here. I'll click start. And the pretest runs. And you can right away see I have a lot more drop in coherence because my shaker gain is much lower. And now you can see my drive predictions. I now require 0.5 volts of drive instead of 0.15. So the pretest predictions kind of tell you all things accounted for, what the shaker accounted for, the mass on the table accounted for, the amplifier gain accounted for. Before you actually jump into your full level test, how much do I think I'm going to need? How hard do I think I'm going to drive the shaker? So it's a really valuable tool. If you're driving a test that's 10% of your shaker's force, you shouldn't see a very high drive value here. If you're using 90% of your shaker's force, then you should be expecting to see a high drive value here. It's a lot of these sanity checks, things that you can just glance at and look at to make sure that things are working well and behaving as expected. All right, then the next two lines here are my two accelerometers. The first is my control accelerometer, and the second is a measurement accel that I've got also on my test structure. And for the accelerometers, it tells us the noise level that it measured, the level that it detected during the pretest, and then that same level in Gs. This is in volts, millivolts, this is in Gs. Then it gives me the signal to noise ratio that was detected. So 13.7, which was above my threshold of 12 that I had set. Then it makes predictions. This next part, the test prediction section, show how much is this accelerometer going to read during my test. So at the start of the test, my ramp up level, it's going to be 0.09 G or volts, which is 0.9 Gs. And then in my full test level, it's going to be 3.7 Gs. Okay, so it gives me a prediction based on that pretest, how hard I'm going to drive the shaker, how many peak Gs my accelerometer is going to respond with. This is the peak G level, and this is the peak voltage level, not the RMS, just to point that out. Then for each of my measurement channels, it does the same thing. It says, okay, based on the dynamics of my structure and where my resonances are and where this accelerometer is located, I'm going to see a different vibration level on my response accels. So this particular accel is going to see 1.1 Gs at the ramp up level and 4.5 Gs at the full test level. Okay, so that's sort of the whole pretest report, everything kind of described in a little bit of detail here. And now I'm going to show you a couple of the errors that are common in pretest reports. The first thing is if something is wrong with the shaker or the amplifier or your feedback accel, you're going to get an error in your pretest report. So we're not going to try and drive the shaker like crazy before we detect that there's a problem. So the first thing I'm going to do is I'm going to unplug my control accelerometer. So say my accel was unplugged or not mounted properly or something to that extent. I'm going to click start my test. And now it's going to start running the pretest. You can see it's not detecting any response vibration from my accel since it's not connected. But the shaker is still being driven or being tickled. And eventually, once it hits my maximum drive voltage that I had pre-configured, it's going to tell me I failed, signal to noise on input 1. So the input 1 never got that 12 dB of signal to noise that it was expecting. And this is how that looks in the pretest. Okay, so that's the most common problem. That means that there's something wrong in your closed loop. You've got something, either the amplifier is not powered on, the amplifier is not connected to the controller, the accelerometer is not connected to the controller or not mounted on the shaker. There's something in that closed circular feedback loop that's not that needs to be fixed. All right, so I'm plugged my accel back in and run one more pretest, and I'm going to go through a little bit of the pretest data here that we see on the screen. So while the pretest is running, the screen populates with the data from the transfer function that I spoke about earlier that tells you your resonances. You can see I've got a resonance here and a few resonances here and a lot more at higher frequencies. And then the middle plot is what I want to focus on here, the coherence, which is what tells you how linear your response was or how controllable your response was. And I mentioned earlier things like, items that are rattling, bolts that aren't secured on fully, that aren't tight enough, electrical noise, that'll all show up as drops in your coherence. So right now you can see my coherence at my low frequency, 10 to 50, 60 hertz is really poor. But my coherence above 100 hertz is pretty good, except for these individual dropouts. Now I can tell you here, looking at these individual dropouts, just looking at the nature of them, one individual spike every, it's actually every 60 hertz. That tells me that, yeah, I've got some sort of ground loop noise problems that I may need to overcome. So one way to overcome that is to increase my shaker's gain. So if that ground loop noise is just inherent to the system and it's not proportional to shaker's gain, then increasing the shaker's gain will get you a better pretest. So let me do that. And I'm going to run another pretest. That noise should get a little bit better now. And that just comes from me knowing my shaker system. Every shaker system has its own quirk, and getting to know your system is important. So now that helped with the coherence at the high frequency. So now the only coherence drop I see is at low frequency, and almost all the time there are certain times where it's a mechanical problem that causes problems with large displacements, which manifests as coherence drop at low frequency. But a lot of the times you see a problem with low frequency because you just didn't drive hard enough at low frequency. The shaker needs more energy at low frequency. Now, the end result of this, if I actually try to run this test, if I click start, it still thinks that it can run the test. It's not predicting that I need a crazy high drive voltage to run. The coherence is good for most of the pretest, so it still let me run. But we're going to see, I'm going to click start here, and we're going to go to my control drive layout, and we'll see the control at low frequency is going to start out pretty poor. It's gonna improve, but it'll start out poor. So keep an eye at 10 to 20 hertz as soon as I click start. Down here at 10 to 20 hertz, we're gonna see you can see the vibe level was a little bit above. It's still a little bit above the reference, and then give it a little bit of time and it'll improve. As the closed loop correction improves, adapts. But that little bit of overshoot, that's all predictable based on that pretest coherence. If you see a drop in your pretest coherence, you're going to have trouble controlling the test, at least initially. So this is the most common problem, is poor coherence at low frequency. And the one tool that we've added in recent 1.5 versions of our SignalCalc 900 software is the auto-shaped broadband. So back in my test setup, under control parameters, under the pretest settings, I'm going to set this from broadband to auto-shape broadband. And now what this is going to do is it's going to automatically add more energy at low frequency where most shakers need it to try and bump up that coherence and try and get a better coherence at low frequency and across the whole test band. And what we'll see, so let me start that. And what we'll see is once we actually start running the test, that better coherence at low frequency is going to get much better. The test results are going to be much better right off the bat as soon as we start the test. So you can see the improvement there. Now my coherence is above 0.8, almost above 0.9 for the whole frequency band, which is exactly what we want to look for. I'm going to hit start. And now as soon as my test ramps up here, we're going to see that the control is much closer to the tolerance line right off the bat from the very beginning of the test. All right, so just to summarize to summarize the pretest, the purpose of the pretest is to detect problems before they happen, to make predictions on whether or not this test is going to be require a lot of drive voltage out of the controller and a lot of energy out of the shaker or out of the amplifier, and to make predictions on whether or not your test parameters, your accelerometers can measure the vibe levels that you're going to test to, and to make predictions generally on whether or not the test will run before you actually run the test. And then the data is all given in the pretest report. And if I'm running a vibe test, the two things I look for are my pretest report, my drive predictions, and then I also look at my coherence for the pretest. If I see dropouts in coherence, that instantly tells me that I may have trouble running the test and that I need to either adjust my pretest settings to get a better pretest, or if that doesn't, the pretest doesn't improve, then I might have something mechanically wrong with the shaker that's going to need some attention before the test can run. I have one question here. Is the pretest different between sign and random tests? So I showed a sign test here. All right, sorry, I showed a random test here, but the pretest, the whole entire pretest process is identical, whether you're running sign or random or shock. Any of our vibe control test types, the pretest is the same. That part of our that part is intentionally left the same, so that no matter what test you do, the first initial run up to the test is the same, and all the markers that tell you whether or not the test is going to run, the coherence, the report, those are all the same between all the test types as well. All right, have another question here. Using an example of raising the gain to overcome low frequency problems, is there an indicator of too much shaker gain, too much amplifier gain? So the only indicator of too much amplifier gain, it really depends on your test, on the sensitivity of your test article. Obviously, the pretest is meant to tickle the shaker. You don't want to be driving as hard as your actual vibe profile is going to be. In terms of the actual quality of the pretest data, there actually is no difference. It doesn't matter if you run at a very high gain or a very or an even higher gain. The pretest data, once you're above a certain noise threshold, you're going to get the same pretest data out of the shaker. So you really have to kind of, it is a little bit, this is why we purposely set the drive voltage level to be very low, 10 millivolts, maybe 25 millivolts at most, so that even if you turn the gain all the way up on the amplifier, you're not going to overdrive anything or risk damaging anything. But it is a bit of an art there to make sure that you don't get, we did display, I didn't really talk about the time history that was displayed. Let me bring up the software here. The time window that's displayed at the bottom here. This time window actually shows you can see how many Gs my control accelerometer is seeing. So I could see during this pretest, my control accelerometer was seeing about 0.2, 0.3 Gs peak. The only difference in the pretest data, if I turn up the gain on the shaker all the way, let me do this. Let me turn the gain up all the way. You'll see that I get the first two plots are going to be identical, but the only difference is going to be my time domain plot, because the transfer function divides the gain, the response by the drive voltage, and then the coherence, is still going to be linear because I'm above my signal to noise threshold. But now, the drive prediction is going to be lower. So you have to look at your time domain, make sure you're not going to be overdriving your shaker. I guess the one other aspect, and I'm going kind of long on this question here because I'm sort of getting more as I talk here, is if you look at your drive voltage prediction during the test, if my drive voltage prediction is really low, if it's below 100 millivolts or 50 millivolts, 0.05 volts, that's a good indication that you should drop your gain on the shaker and rerun the pretest. Because this, you want a healthy drive voltage going to your shaker. You don't want to be driving in the noise. I have another question here. Is the pretest broadband excitation spectrum flat or shaped based on the 0 dB profile? The pretest excitation is flat. It's not based on the 0 dB profile. That is for the standard broadband excitation. Now, this auto-shaped broadband, it starts out as flat, but then it adds energy at frequencies where it's needed, at low frequencies as needed. So it ends up not being a flat excitation. But initially it starts out as flat, and then it basically takes energy from the high and puts it into the low. But it's not based on the 0 dB profile. Thank you. If any more questions, please reach out to myself, Raman Sridharan at dataphysics.com, or your local data physics rep. And you can find a lot more information on our products at dataphysics.com.